Okay, this is a continuation of section 9.4 on convergent tests. And this is page 16 in your packet, class notes packet, and we're going to now go over the p-series and the polynomial test. So the p-series test, let's first of all define what p-series is. A p-series or hyperharmonic series is an infinite series and it has this particular form. So you have 1 over k raised to the p power, right? So the k is usually going to just stay as k, and p is what is the number that's going to get filled in. And so it's got this particular form. And so here are some examples. When p is equal to 1, this is actually the harmonic series. And so you would have the pattern of 1 plus 1 over 2 plus 1 over 3 all the way to 1 over k. And then if p is equal to 2, you have 1 plus 1 over 2 squared plus 1 over 3 squared plus all the way to k squared. And then if p is equal to 1/2, it'll look like 1 over the square root of k. So this is the same thing as 1 over k raised to the 1/2 power, right? So they've written this as a root, and this one is a fractional exponent, right? So those are equivalent. And so these are some examples of the p-series. Okay, so here's the p-series test. And what it states is that if you have a p-series, if the p, so just think of p as the power, if p is greater than 1, then it converges. And if p lies in between 0 and 1, and also including 1, then it will diverge. And all of this can be shown by the integral test, but it's just a lot easier with this p-series test rather than using the integral test. Okay, so if you look back up here, this one is p is equal to 1, so this diverges. This one is p is equal to 2, which is greater than 1, so this converges. And this is p is equal to 1/2, so that means that it diverges. Okay, so let's look at a few more examples down here at the bottom. So using the p-series test, determine if the series converges or diverges. So I'm going to rewrite the fourth root of k as k to the 1/2 power. So here p is equal to 1/4. I meant k to the 1/4 power. So p is equal to 1/4. So that lies in between 0 and 1. Therefore, this series diverges. Okay, and then for the next one, we have k raised to the negative 4/3. So I can rewrite this as 1 over k to the 4/3. So p is equal to 4/3, which is greater than 1. So this one converges. So this is a nice test because it's very quick and simple. Okay, turn to page 17, and we're going to look at the polynomial test, which is not in the textbook. All right, you're given a rational function p of k over q of k, where p of k and q of k are polynomial functions of the degree n and d. So I'm using the numerator's degree as n and the denominator's degree as d. And so if you have this as your kth term and you're looking at the series, then this is the conclusion. If it converges, that means that the numerator's power plus 1 is less than the denominator's power. And it diverges if the numerator's power plus 1 is greater than or equal to the denominator's power. Okay, so let's use the convergence or the polynomial test and look at these problems. So this is of the form that we like. It's 1 over k. So the numerator's power is 0, right? Because it's to the 0 power, and that's why you just get a constant. The denominator's power is 1, right? So I'm looking at it with a k. So the numerator's power plus 1 is 0 plus 1, which is greater than or equal to the denominator's power of 1, so it diverges. And that's consistent with our p-series, and this is the harmonic. Okay, the next one is the 2k over k to the fourth plus 1. So the numerator's power is 1, the denominator's is 4. So if you take n plus 1, which is 1 plus 1, the numerator's power is 1, and the denominator is 4, 2 is less than 4, so it converges. Okay, I'd like you to pause this video and try C and D. Okay, here are the answers. So for C, your numerator's power is 1, and then the denominator's is 1. You add 1 to the numerator, and it's greater than or equal to 1, so it diverges. Okay, for D, your numerator's power is 0, and you add 1 and compare it to the denominator's power, which is 3, which is less than, 1 is less than 3, so it converges. Okay, now in example 6, I would like you to pause the video and try these examples and then come back and check your answers. And so for these problems, it's not specific which one you should use. So you need to go back to all the different tests that we've gone over in this section and previous sections and see which one will apply the best. All right, so pause the video and go through these problems, and then I'd like you to check your answers. Okay, so for A, this is a version of the harmonic series. So it diverges. This 3 and the 5, it will not have any effect in the long run, and so it's same as 1 over k, and so it diverges. I can also use a polynomial test and show that it also diverges. So the numerator's power is 0, and then I add 1, and that is greater than or equal to the denominator's power of 1. Okay, so for the next one, I'm going to look at the divergent test. And so I take the limit of 1 over e to the 1 over k as k goes to infinity. And this is going to equal 1 over e to the 0, which is 1, which does not equal 0. So then it diverges by the divergent test. Okay, for C, I use the integral test. And the reason is that this is easy to integrate. And so I did a u sub on this. And then I take the limit and evaluate, and I get 1 over 2e, which means that the integral converges, so then the series converges. And then the last one, I use the polynomial test. So I have 2 plus 1 is greater than or equal to 2, so it diverges. I can also use the divergent test on this and take the limit of the kth term as k goes to infinity, and it equals 1, which does not equal 0. So that means it diverges.